This is the last section in chapter 1, and this talks about logarithmic functions. In the last section, we learned about exponential functions, and logarithmic functions are inverses of each other. So we're going to first start talking about what an inverse is, and then look at how that leads us to logarithms. Logarithms can have lots of different applications. The one that's most relevant for this class has to do with solving problems that involve doubling time and so forth. Okay, in order for a function to have an inverse, it has to be what we call one-to-one. So for a one-to-one function, basically, each domain value corresponds to exactly one range value. Okay, so like it's probably easier to look at the one that's not one-to-one. So like here, we have a range value of 2, and that corresponds to both 4 and also -4. And because of that, it would not be considered to be one-to-one, and therefore it would not have an inverse. If we look at this one here, though, 2 only has one value, one x value that corresponds with that, and so it would be one-to-one, and it would therefore have an inverse. Okay, any continuous function that's either increasing or decreasing for all domain values is considered to be one-to-one. So as long as it's either always increasing or always decreasing, then it is going to be one-to-one, and it is going to have an inverse. If it increases for some domain values and then decreases for others, then it's not going to be one-to-one. So we have a test, just like we have a vertical line test to determine if a graph is a function. We have a horizontal line test, and it actually tells us that whether or not it's one-to-one. So if a horizontal line touches the graph more than once, then the graph does not represent a one-to-one function. And if we look back here, you can see that a horizontal line, which is what's drawn here, would touch it more than one time, and therefore it would not be a function. It would not be one-to-one. Okay, so if a function is one-to-one, then the inverse of f is the function that's formed by interchanging the independent and dependent variables. So the notation for an inverse is f to the -1. It's not saying that you're raising it to the power of -1. This whole thing just is the notation for an inverse. So basically, it interchanges the dependent and independent variables, or it interchanges your x and your y. So like here we have the point A, B. If this is a point on the original graph, then if we switch the domain and range, we would have B and A. That would be a point on its inverse. Okay. And if the function is not one-to-one, then it does not have an inverse. Okay, so if we look at the exponential function y equals 2 to the x, you remember that looked something like this. Okay, so it was a growth function. It would be increasing for all domain values, and therefore it would pass the horizontal line test, and it would have an inverse. So we want to be able to find that inverse. So the inverse comes about by interchanging the x and the y. But if we interchange the x and the y and then try to solve it for y, we actually have to introduce something called the logarithm to do that. So the logarithmic graph is actually the graph of the exponential function. Because of the way we interchange the x and the y, it's the reflection of the exponential function in that line y equals x. So if I have the point, say 2, 4, then the point 4, 2 is going to be on the inverse. If I have the point 0.10, then 0, 1, then those are going to correspond. So there has to be that correspondence there. So we have the point 3, 8 on the original graph, so we would have the point 8, 3 on the inverse. Okay, when that happens, the base of the exponential function has to be the same as the base of the logarithmic function. Okay, so y equals 2 to the x and y equals the log with a base of 2 are inverses of each other. Okay, the domain of a logarithmic function is the set of all positive real numbers. So if you look back at the graph here, you can see that the exponential function had a horizontal asymptote on the x-axis. The logarithmic function actually has a vertical asymptote here at the y-axis. Okay, so the logarithmic function never crosses the y-axis, so it's not defined over here for negative numbers. So you can't take the log of a negative number is what happens because of that. So we do have to apply some domain restrictions in order to avoid that. The range itself, again, looking at that graph, it goes forever in the negative infinity direction. And then even though it doesn't grow rapidly, it is still continuing to increase and therefore going to positive infinity. So there is no restrictions on the range. So the range would just simply be the set of all real numbers. Okay, you need to be able to go back and forth between logarithmic and exponential form because that will be beneficial in terms of some of what we're going to be doing. Anytime you're going from logarithmic form to exponential form, you basically are just going to make a little circle here. If you'll just remember, always start with the base of your logarithm. Okay, so I'm going to write the 5. I'm going to raise it to my exponent. So the exponent is always sitting over here by itself. So I'm going to write it as 5 to the third, and then it's going to be equal to the 125. This would be your exponential form that corresponds with this logarithmic form. So this one, again, start with the base of 4, raise it to the 1/2 power, and then that's going to be equal to 2. Here I'm going to start with a base of 3, raise it to the -3 power, and then that's going to be equal to 1/27. Okay, here's some for you to practice if you want to pause it and give it a try. Okay, the logarithmic form for this first one would be we have a base of 3, so it's going to be 3 squared is equal to 9. This one we start with a base of 4, so 4 to the 1/2 is equal to 2. And then this one we're going to have 3 to the -2 is equal to 1/9. Okay, we'll circle it back around. Okay, these were going in the reverse direction. So we're given our exponential form and we're going to write it back in logarithmic form. So when we're doing that, keep in mind where everything belongs. Okay, so the base is going to be here, whatever it's equal to. So I'm going to call this the answer. And then it's going to be equal to the exponent. Okay, so when I'm looking at this, I'm going to write, and I'm putting it in logarithmic form, my base is 3, so it's going to go here. My answer is the part over here on the other side of the equals, so that's going to go here. And then your exponent is going to be whatever your exponent is, it goes over here on the right side. Okay, and if you're ever not sure if you did it right, just go back and do your circle. So 3 to the -2 is equal to 1/9. So that does check. Here I'm going to do the log. My base is 125. It equals 25, and my exponent is 2/3. And then the last one, I'm going to have the log with a base of 2. It's equal to 256, and my exponent is 8. Okay, here's some for you to try. Okay, this one's going to be log, my base is 7 here. It's equal to 49, and my exponent is 2. So this one is a little bit turned around, so just be careful with that. But again, if we check it, 7 to the second is equal to 49. That's what we get here. This one's a little tricky because anytime you see a square root, that's equal to the 1/2 power. So that's the same thing as 9 to the 1/2. So the logarithmic form for this would be log a base of 9 of 3 is equal to 1/2. Okay. And then this one, log, we have a base of 3 is equal to 1/3. And this would be, the exponent's going to be the -1. So the base is always pretty easy to figure out. The exponent is always the part that's by itself. Like in the logarithmic form, it's the part that's by itself. So that would, the 2 should represent your exponent. The 1/2 should represent your exponent. The -1 should represent your exponent. Okay, here we've got, you're asked to solve a logarithmic equation. We're solving it for, in this case, the base of b. So anytime you have just a log on one side, my suggestion would be to put it in exponential form. And that's why knowing how to go back and forth between those is important. So if I put this in exponential form, it's going to be b to the second power is equal to 100. So our circle's kind of looping back in a little different way because of the order of our equation, but basically b to the second is equal to 100. If I take the square root, I'm going to get b is equal to, and we don't really have to consider the plus or minus case on that square root just because it is a base for a logarithm, so it's going to be a positive number. Okay, here's another one. It's a little mini equation, and you're asked to solve for x. So this one, if I just put it in exponential form, I'm going to do 6 to the 5th is equal to x. And that's actually already solved for x. I don't really have to do any more than just put it in exponential form. And you could certainly do 6 to the 5th is 7,776. Okay, we've got a couple little mini equations here to solve. So I would suggest that you try them. Okay, for part A, we want to put this in logarithmic form. And if it makes you like uncomfortable to do it this way, just rewrite it. So log the base of 9 of 27 is equal to y. So rewrite it so that the log is on the left side, and then you can do like your circle and everything is fine. So we have 9 to the y is equal to 27. Okay, this one actually is going to take a little bit more work to do because I'm going to replace 9 with 3 to the second power because I need to get their bases the same in order to solve this problem, and both 9 and 27 can be written with the base of 3. So 3 to the second is 9, 3 to the third is 27. Okay, so one of the properties that we've looked at recently said if our bases are the same, then the exponents must also be the same if they're equal to each other. Okay, so this is equal to, multiply those exponents together, so that's going to be 2y. Okay, so because the bases are alike, that means that 2y has to be equal to 3. So y is going to be equal to 3 over 2. All right, b, if we look at this one, it's already on the left side, so we're just going to circle it around. So we'll have 3 to the -1 is equal to x. Remember that anything to the -1, we can bump that to the denominator. So that means x would be 1/3. And then for part C, we're going to have b to the third is equal to 1,000. So to get rid of a cube, we're going to do a cube root. So b is going to be equal to 10. Okay, we have some properties of logarithmic functions that I would suggest you refresh your memory on. You should have seen them at some point in your previous math classes. The first one just says that the log with any base of 1 is equal to 0. If you think about that, if we were to put this in its exponential form, we would have b to the 0 is equal to 1. That's true regardless of what base we have. So any base raised to the 0 power is equal to 1. Okay, if we have one like this and the two bases match up here, then what happens is basically all of this cancels and you're just left with that 1. And that's the same thing if I put it in its exponential form, it would be b to the first is equal to b. And so that should always be true regardless of what b is. Same thing here. If I put it in its exponential form, b to the x is equal to b to the x. So this number 2 is just a special case of number 3. But again, anytime that these two bases match up, those are going to cancel out and you're just going to be left with that exponent. Same thing here. If this base and this base match up, then you're just left with the exponent there. And we have these properties where we can break apart logarithms. So if I'm taking the log of two things that are multiplied together, I can split this product up into two separate logarithms that are added together. Same thing with division. I can break that up so that it is subtraction of two logarithms. This one, if I have it raised to an exponent, then I can actually bring this down in front and make it easier to work with so that exponent can come down in front. And then finally, if I have two logarithms with the same base that are equal, then that means that these two arguments here must be equal as well. So we're going to do a few examples using these. Okay, so this one's asking us to write the expression in simpler form, which basically means we're going to break it up. Instead of being multiplied and divided, it's going to be added and subtracted. Okay, so I'm going to deal with the division first. So I'm going to rewrite this as the log. Don't change the base, leave it like it is. So we're going to have the log with the base b of xy, and since it's divided, when we break this apart, it's going to become the log base b of tz. Okay, so we're going to subtract those. When this would had a single logarithm and they were divided, we can break it apart into two logarithms that are subtracted. Then looking at this, we've got two that are multiplied together here and then two more multiplied together here. So we can split this one up and do log base b of x plus the log base b of y. And then I'm going to subtract from that the log base b of t and the log base b of z. And you can either leave it like that or you can go ahead and distribute that negative. So we would have minus log base b of t and then minus log base b of z. So that would be it in its simpler form. Okay, this one, if we're going to write it in its simpler form or its expanded form, in order to be in its expanded form, you won't have any exponents. So if you remember, the exponent can be brought down in front to make it easier to work with. So when I do that, I'm going to have 4 log base b of xy. We're not finished expanding this because we have two things multiplied together. So what I'm going to do is I'm going to break this logarithm apart. So I have log base b of x, and then I'm going to add, because these were multiplied, I'm going to add here log base b of y. And you can distribute the 4 through if you want to do that. Okay, and so that would be our answer. Okay, this one, we do have one property to use. So we talked about if we have like bases, the base on the exponential function and the base on the logarithm, if they're the same, then they can cancel out. But only if they're like directly side by side. We've got this x here in the middle of that we need to do something with. So what we're going to do is we're actually going to bump that up as an exponent. So sometimes it's better to bring it down, and other times it's better to push it up as an exponent. This is one of the cases where it's going to be better to push it up as an exponent. So instead of that x being down here in front of the log, we're going to push it up as an exponent for the base of b. Okay, so now we've got these two side by side with the same bases. So that's all going to cancel and just leave us with b to the x. All right, so here's some for you to try as far as writing it in simpler form. Okay, this first one here for a, you would have the log base b of r minus the log base b of st. And then you do want to break that apart. So this would be the log base b of s plus the log base b of t, because these were multiplied together, so we'll break them apart to be addition. And then we can go ahead and distribute that negative. And this is just a helpful tip. If it's coming from the denominator, then it should end up with a negative in front of it. So see how the s and the t both come from the denominator? So they're both going to end up with negatives in front of their logarithms. All right, b, we've got an exponent here, so I'm going to bring that exponent down in front. So 2/3 log base b of rs. And then we know that that r is divided by s. So what I can do is I can break that apart into subtraction of the two logarithms. And if we wanted to, we could distribute the 2/3. Okay, here is an example of a logarithmic equation that you could solve using some of the properties that we've talked about so far. So we have two logarithms that are joined by addition. So sometimes it's helpful to be able to combine these two together. So if I'm going to combine those two together, then I'm going to combine them as multiplication. So instead of having two logarithms, I now have one, but I have to multiply these two things together. Okay, so I have just log on one side, so I'm going to put this in exponential form. So 4 to the third is equal to x plus 6 times x minus 6. Okay, 4 to the third is 64. And if I FOIL this out, the inner and the outer actually cancel, and I just have x squared minus 36. So if I add 36 to both sides, I'll have x squared is equal to 100. So x would be equal to either plus or minus 10. And I have to be careful about this minus, because if I put a negative here, that would give me I would be taking the log of a -4. I can't take the log of a negative number, so I do have to eliminate that negative. So x is just going to be a positive 10. Okay, so a lot of the logarithms that we work with are special logarithms. You have a special key on your calculator. So you may have noticed that you have an LOG key and you have an LN key on your calculator, and those are on the far left side of your calculator. So if it is a log and it doesn't specify the base, then it's a base of 10, and it's called the common log. If it's ln, then that's the same thing as log with that special base of e. Okay, so those two things are equivalent. We don't write it like this. We write it like that because it's that special that we use that one in that way and give it a special name. So we've got the common log. So if there's no base indicated, it's log. But if it's ln, then it's a base of e. Okay, if we look at this example solving, this is actually similar to the one we just did using log. Okay, we've got a minus, so when I combine these from 2 into 1, I'm going to combine them as division. All right, so then I'm going to put it in exponential form. Keep in mind the base of ln is e, so it's going to be e to the first power is equal to x plus 1 over x. Okay, so we're going to cross multiply at this point. And this one's going to be a little complicated to get the x by itself. I'm going to move all the terms that have x in them to one side. I'll factor out the x as a GCF. And then I'm going to divide by this part here. So my answer is 1 over e minus 1. Okay, here's one for you to try. Let's try to simplify each term before we combine them together. So if we bring the 3 up, we're going to have the log base b of 2 to the third. And then we're going to have log base b of 25 to the 1/2 minus log base b of 20 is equal to log base b of x. Okay, let's clean this up a little bit. So 2 to the third would be 8. 25 to the 1/2, that's the square root of 25. That's going to be 5. Just recopy in here. Okay, so we've got 3 logarithms that need to be combined together into one. Okay, so these two are added, so I'm going to multiply the 8 and the 5 together. And then this one's subtracted, which means it's going to need to be divided. All right, we'll clean this up a little bit. So that's 40 over 20, so 2. Okay, so if everything else is the same, then x must be equal to 2. All right, here's one for you to practice with. Okay, so very similar to what we just did, we're going to combine these two into one logarithm by multiplying those together. This one's a little different because it does have logs on both sides. So because it's got logs with the same base on both sides, we can actually just disregard those and look. It's not really that they cancel, so I don't want you to say cancel, but basically we have a property that says that if this part's the same with the same base, then this has to be equal to this. So that's going to be x squared minus 3x is equal to 10. So we have a quadratic. So with quadratics, we always want to get that equal to 0. Okay. And then if we can factor it, we will. So we want to see what multiplies to give us 10 and subtracts to give us 3. So that would be 5 and 2. So x is going to be 5 or negative 2. But if we put negative 2 in here, we can't take the log of a negative number. So we're going to have to throw that one out and just give 5 as your answer. Okay, this is just involving finding the key on your calculator to evaluate these. So hopefully you have found that and try that. So if I take the log of of the 5,287. You can see what I get there. The ln of this number gives me this. And then when I try to take the log of negative 2.88, I do get an error message that says non-real answer or just says error. The reason being I can't take the log of a negative number, and therefore that's why the calculator is going to give me a negative, going to give me an error for my answer. Okay, here's some more if you would like to try those and their answers on those as well. Okay, if we wanted to solve one like this is a common log because there's no log base listed there. So we're going to have an understood 10. So it's going to be 10 to the negative 1.864, and that's going to be equal to x. And that would actually be our answer. We just need to put that in the calculator. So x is 0.013, it's like 37. Okay, if we have one like this, we've got the ln of x is equal to 3.416. ln has an understood base of e, so it's going to be e to the 3.416. That's going to be equal to x. And then just put that in your calculator to get your answer. Okay, so it looks like 30.447, and then the 8's going to round the 3 up to a 4. For your answer. Okay, again, here's some to practice on. In each case, this ln has a base of e, so it's going to be e to the negative 5.062, so 0.0063. And then this one, log, has a base of 10 if it's not specified. So x is going to be 120.8092. All right, we're going to use all this to be able to solve equations like this one here. So we've got 10 to the x is equal to 15. So we have a base of 10. So that sets us up nicely to use a common log to do this. So if I take a common log of 10 to the x, and I do that for both sides, then we know that a common log has that base of 10, and that means those cancel. So x is just simply going to be the log of 15. So 1.1761. Okay, if we have one like this, 5 to the x is equal to 11, we could take a common log. Probably more conventionally, we actually just do the ln. So ln of 5 to the x is equal to the ln of 11. And there are multiple ways to proceed. So if you've learned it a different way, that's fine as well. But what that does is it lets us apply the logarithm property that brings the x down in front. And that's very helpful because if we're trying to get x by itself, then all we really need to do is divide by the ln of 5 because this is just a number. Okay, so x is going to be the ln of 11 divided by the ln of 5. So it looks like 1.4899. Okay, here are a few for you to practice. This one is set up nicely for a common log. So we'll do the log of 10 to the x is equal to the log of 7. Again, if it's a common log with a base of 10, then we're left with x equals the log of 7. So 0.8451. This one with a base of e, certainly we want to use ln. Okay, and because ln has a understood base of e, that means that those two cancel. So anytime you see ln and e paired directly side by side like that, they're going to cancel each other out. So x is going to be the natural log of 6. So that would be 1.7918. And then this one, it really doesn't matter because you don't really have one of those special bases. So typically we'll just use ln. So ln of 4 to the x is equal to the ln of 5. Bring that x down in front like we did in the example earlier. Divide by ln of 4. And so x is going to be the natural log of 5 over the natural log of 4. Okay, so x is going to be 1.16. Looks like that's going to bump it up to 10. Okay, so sometimes it's important to be able to change bases. So if we're going to change bases, we have this change of base formula, and that just says that the log with a base of b. So you're really only going to use this in cases that's not a common log or a natural log. So if I had like a base of 2 or 4 or 3, then I might want to write it like this so that I can get a value for it on my calculator. But it's essentially the log of x and then the log of b. Okay, sometimes we need to use logarithms to compare doubling times and even to find doubling times. And that's important because obviously an investment with a shorter doubling time has a higher rate of return, and these logarithms can be helpful in finding that. So let's look at this example. How long to the next whole year will it take money to double if it's invested at 5% compounded annually? Okay, so since it's compounded annually, that tells me that we're going to be working with this formula that we have used already. But we're going to be, because it asks for how long, we're actually going to be solving for the t, and we're going to be given everything else. So how long will it take the money to double if it's invested at 15%? So our rate is 0.15, and it's compounded annually, so that means m is 1. Okay. So we don't even know what the principal is, but if we want it to double, whatever we start out with, we're going to call P. So if we want it to double, that's going to be 2P, okay? So that means we're going to start with just P. We want the amount that we end with to be 2P, and we'll plug in everything else. So I have 0.15, M is 1 to the 1 times T. All right, the thing that's good about this is, well, first of all, let me clean this up a little bit. This inside would just be 1.15, and that would be to the t. We can divide this p away, so it's not really going to be a part of our equation. It's just going to be 2 is equal to 1.15t. Okay. All right, so we're going to take the natural log of both sides like we've done on some of our previous examples that weren't word problems. That'll let us bring the t down in front. Then I'm going to divide that away so that I get the t by itself. So t is going to be the natural log of 2 divided by the natural log of 1.15. So t is 4.96. Right, and it says to the next whole year. So basically it's going to take about 5 years for this particular investment to double. Okay, here we have another practice one. How long, so we're finding the t, will it take it to triple if it's invested at 13%? So R is 0.13, compounded annually, so my M is going to be 1. Okay, so we're going to use that same formula we've worked with before. And the amount This time we want it to triple, so that's going to be 3 times what we start with, which is the original p. The rate is 0.13 over 1, and then to the 1 times t. So we're just going to clean this up a little bit, divide away those p's so they're out of the way for us. Okay, so then because the t is in the exponent, and that's one thing I maybe haven't said as clearly as I should, the reason that we have to use these logarithms to solve equations like this is because the variable is now in the exponent. So in order to get that exponent down where we can actually work with it, we have to take a logarithm. Okay, so that means that we can bring the t down in front as we've done before. And this point, hopefully it's starting to kind of be routine. That's why I'm going a little bit fast with this part. So t is going to be the natural log of 3 divided by the natural log of 1.13. So 8.99. So basically 9 years for that investment to double. Okay, that's the end of this section. Thank you for listening.